Hello viewers, welcome to this NPTEL MOOC course on mathematical portfolio theory. In this week's classes, what we will do is we will look at the basics of probability theory. So, in the first lecture today, we will do probability theory in general in both discrete and continuous time, and we will talk about random variables. This will be followed by a discussion on expectation, variance, covariance and correlation coefficients, and then we will talk about two important distributions, namely the binomial distribution and the normal distribution, and we will conclude this discussion by the end of the week with a discussion on linear regression. So, we start off our lecture number 1 with basics of probability theory, and the first thing we will do is we will do probability space and their properties. So, what we will do is that we will first essentially look at the finite discrete space, and then we will look at a general probability space. So, finite discrete probability space. So, we start off with a definition of what is a finite probability space. So, a finite probability space is defined as a pair omega p, where the first component omega is a finite non-empty set called the sample space, and the second component p is a real valued function which is defined on the set of all subsets of omega, and this p is called a probability measure on the sample space omega. So, next we look at some of the properties of this measure p. So, the probability measure p, which is defined above, will satisfy the following three properties. So, satisfies the following properties. The first property it satisfies is that for all a in omega, that is all subsets of omega, the probability measure of a will lie between 0 and 1, both included. So, here I make a note that all such a which are subset of omega are henceforth going to be called events. The second property, which is the probability of omega, and this is given to be equal to 1. And the last property of the probability measure is that if A1, A2 all the way to An are pairwise disjoint events, then the probability of union of I equal to 1 to n, this is simply going to be the sum of probability of the I is equal to 1 to n. So, this brings me to the next definition, and this is sort of at a more elementary level than any event A. And so, I start off with that omega be a finite sample space. Remember, we are talking about the finite probability distribution. So, let this be a finite sample space. Then, for all omega belonging to omega, that means each element of the sample space omega, the event of this singleton event given by this omega is called an elementary event. So, accordingly, once we have defined what is an elementary event, so accordingly we can assign the probability. Remember, the elementary event is also an event. So, we can assign a probability which we will denote by p subscript of omega for each elementary event omega, such that, and obviously it is going to satisfy the probability or the property that lies between 0 and 1 both inclusive, and summation of p omega equal to 1, and obviously this omega must be omega belonging to the sample space big omega. So, once we have both these things set up, the probability measure and the probability of an elementary event, so therefore, we can define the probability measure p, which you have already introduced along with the 3 properties. So, we will define the probability measure p in terms of elementary events as probability of the elementary event little omega, this is p of subscript omega that we have already introduced. Further on, I can make another statement that the probability measure p in terms of an event. So, let us go back to a generic event A will be the sum of probabilities of all the elementary events in A, and is accordingly given by probability of A is going to be simply the summation of probability p subscript omega, where my omega is a member of the event A. So, this brings me naturally to 2 more definitions. The first one is, so now that I have defined all these probabilities for each elementary event, so this particular set P subscript omega for all omega belonging to omega. So, this set is called a probability distribution, and please do not confuse this with a distribution function that we will discuss in the later part of this lecture. So, the other definition that you have, so here now once I have all the p omegas, so I am now in a position to define what is known as the probability mass function. So, the real valued function f from omega to r defined as, so this is going to be f of the elementary event omega, since it is defined on the sample space, equal to p omega. So, if I define this real valued function, this is called the probability mass function. Okay, so continuing with our definition, let us move on to the notion of independence of events. So, accordingly, the collection of events A1, A2 all the way through AN are said to be independent if any subcollection of these n events. So, if any subcollection which I will denote as AS1, AS2 all the way to say some ASK of events. So, that means there are S number of members, including the possibility of course of the collection of all events, right. So, this means including the collection of these events, this will satisfy the following. So, this subcollection has to satisfy the following property, that the probability of the intersection of AS1, AS2 all the way to ASK, this is simply going to be the product of the probability of ASI, I is equal to 1 to k. That is, it is probability of AS1 into probability of AS2 all the way to probability of ASK. All right. So, once we are done with this definition of independence, we move on to the definition of what is known as a random variable. So, this is a very important component from the context of the course. So, eventually what we will do is that we will talk about random variable, and one of the main random variables that we will look at during the course is going to be the random variable representing the return of any asset, which is in turn going to drive the notion of expected return of an asset and the risk of an asset, and which will then be extended to talk about what is going to be the expected return of a portfolio and what is going to be the risk of a particular asset, with the return for each of the asset over several time intervals being considered as the random variable. So, accordingly we need to give a great amount of importance to what is going to be the definition of the random variable, both in case of the finite discrete probability space and in case of a general probability space. So, accordingly we will now start off with the notion of random variable. So, random variable is essentially a real valued function, and typically we denote the random variable x. So, a real valued function x from omega to r, that is, it is defined on a finite sample space omega is called a random variable on omega. So, accordingly, if x is a random variable on a finite probability space, which you denote by omega p, the sample space and the probability measure, and let my finite sample space omega have n number of elements, omega little omega 1 through omega n, with x taking a finite number of possible values, say x 1 through x m, which will put them as a set fancy A. So, this is going to be x 1 through x m. So, remember that x is a random variable from omega to r. So, basically for each omega 1 through omega n, the random variable x is going to take some value. So, that means that the random variable x can take only a finite number of values, and here we are looking at a setting where suppose that they take m number of finite values, and those I will designate it by x 1 through x m. So, that means each of those x 1 through x m is going to be equal to capital X of one of the omega j's. So, accordingly, so once we have set this this set A of the random variables it can take, so then for each of the xi's, that means this x 1 through x m, we have the event, and this why I am calling it an event will become clear soon. So, this x can take any one of the values x 1 through x m. So, the event that x equal to x I, this is going to be nothing but all those collection of omega j such that x of omega j is equal to x I. So, that means all those omega j's in the sample space which takes the value x I will be bundled together and represented as the event of x equal to x I in the chain bracket. So, this implies that the event that x is less than or equal to x I, this is going to be all those omega j's such that x of omega j is less than or equal to x I. Alright. So, just to wind this up, I will just say that further the random variable x, this describes the probability measure. So, I am bringing the probability measure into the picture again. So, describes the probability measure fancy P, but with a subscript x on the set A by probability subscript x of little x I. Remember, this is on the set A. So, A is basically now working like some sort of a sample space, and this is going to be nothing but probability x equal to x I, and this is called the probability measure defined by the random variable x. So, accordingly, the function small f from A to R, just like we had defined the small f earlier to defining the probability mass function, defined by f of x I is equal to probability x equal to x I, is called just like before, this time also we are calling this as the probability mass function of the random variable x. So, here we specify that is the probability mass function for the random variable x. So, accordingly, we now have a definition. Now, once we have this probability measure and the probability mass function for x, so naturally we have to talk about independence. So, the collection of random variables x 1 all the way to x n, some n number of random variables, are said to be independent if the probability of x 1 is equal to some x 1 all the way to probability of x n is equal to small x n. This is simply going to be the product of probability of x I is equal to little x I is equal to 1 to n. Alright, so what we have done so far is we have looked at what is a finite probability space, and we looked at what is a probability measure, and we talked about random variables, and we talked about independence of events as well as the independence of event under the random variable x. So, now we need to move on from a finite discrete probability space to a general probability space to have a more general idea with a particular emphasis on a continuous probability space. So, accordingly we now start on the general theory of probability, and we will now move on to two things. One is the infinite discrete probability space, and we will talk about continuous probability space. So, we begin with a definition. So, as before, let omega be a non-empty set. Now, in the previous case we had only talked about a probability space in terms of the sample space omega and the probability measure p. However, we now need to have an additional term here, and accordingly we introduce what is known as the sigma algebra. So, accordingly we can write that a non-empty collection which are denoted by sigma, and this is the collection of subsets of the sample space omega, is a sigma algebra if it satisfies the following properties. The first property is that omega belongs to this sigma algebra. Second, if we have, so this is the second properties of closure under countable union. So, if A1, A2 all the way is a sequence of elements of sigma, then the union of all these AIs I equal to 1 to infinity, this also belongs to sigma. And the third property is closure under complement, which says that if A belongs to sigma, then the complement of A also belongs to sigma. Alright, so this brings us to the definition of a measurable space. So, we will first have to define what is a measurable space, and then we will define what is a probability space, just like we had done in the finite discrete case. So, first definition that is on what is a measurable space. So, a measurable space is the pair of omega along with this sigma algebra sigma, where omega is a non-empty set and sigma is a sigma algebra of subsets of omega that you have just defined. So, this takes care of what is a measurable space, and now we are in a position to talk about what is a probability space. So, a probability space is a triple. So, you recollect the earlier probability space only had omega and p, but now we have omega, sigma and p with the non-empty set omega being the sample space and sigma being a sigma algebra of subsets of omega whose elements are called events, and p being a real valued function defined on sigma and called a probability measure. So, basically the probability space is this triple omega sigma p, where my omega is the sample space, sigma is a sigma algebra and p is a probability measure. So, now that we have introduced what is a probability measure, so we need to talk about properties similar to the case we had done in case of the finite probability space. So, here accordingly, so what are going to be the properties of p? So, now the probability measure p as defined above in case of a general probability space. So, I have to specify that. So, as it is defined above, this satisfies the following properties. The first of property is the range. So, as before for all a event a in omega. So, 0 less than or equal to p a less than or equal to 1. So, the probability lies between 0 and 1 both inclusive. P of omega is equal to 1. So, these two properties are the same as before. However, in the last case, since now we can have an infinite set. So, we will have if a1, a2 and so on is a sequence of pairwise disjoint events, then the probability of union of I equal to 1 to infinity, which was earlier I equal to 1 to n, this is going to be summation of probability I is equal to 1 to infinity. So, basically now we can say that a probability space here is given as omega sigma p, where you have specified that the omega is a non-empty set or the sample space and sigma is a sigma algebra whose properties have been enumerated, the three properties, and the probability measure also has been enumerated in terms of its three properties. Okay, so let us now come to the topic of distribution function, and we will first of all begin with the motivation of why one must make use of distribution function, and then we will move on to the definition of distribution function in the paradigm of continuous probability space. So, accordingly we make the statement that so distribution function, so we just give the motivation to begin with. See, what happens is that in case of a finite or discrete probability space, the probability measure one typically described using the probability mass function, which I will denote by PMF, and you would recall that this was f of little omega was probability of the elementary event omega, is not easily extendable to continuous probability. And so, because of this reason, so accordingly it is for this reason that we introduce the concept of probability distribution function. So, this naturally brings us to the introduction of the definition. So, a real valued function f from R to R is called a probability distribution function if it satisfies the following three enumerated properties. So, the first property is that f is non-decreasing. So, this means that if s is strictly less than t, this will imply that f of s will be less than or equal to f of t. The second property is that f is what is known as right continuous. So, that is a limit of f of t as t tends to a plus is f of a. And the last property is that f satisfies limit f of t as t tends to minus infinity is equal to 0 and limit f of t as t tends to plus infinity is equal to 1. So, based on this definition with this three property of non-decreasing, right continuous and basically the limit as t tends to minus infinity and plus infinity, we are now in a position to state two results. So, the first result state the following, that let P be a probability measure on R, then the function f with subscript p to identify with the probability measure from R to R defined. So, it is a particular function that I am defining in terms of the probability measure p. So, this function f p from R to R defined as f p of t is equal to, so I am defining this as probability of the interval minus infinity close interval t is qualifies as a probability distribution function and is called the distribution function of p. And the second result that I want to state is the following, that let f from R to R be a distribution function as defined in part 1. So, this be a distribution function, then there exists a unique probability measure P f on R whose distribution function is f. So, that is that if you are given a distribution function, then there will exist a unique probability measure whose distribution function is f. So, that means when you are given an f of t, you can find a probability measure P f such that P f of minus infinity t this is equal to f of t. So, the next thing is that we can now move on to the concept of density functions. So, we have the definition is the following: a probability measure P or equivalently, in light of the results 1 and 2, I can talk about a measure P and equivalently a distribution function f p is absolutely continuous if it has a density function f from R to R which is non-negative, to confirm with the non-negativity of probability. So, which is non-negative such that f p of t is equal to integral minus infinity to t f x dx, and so accordingly probability of the interval a b, this is going to be integral a to b f of x dx. Alright, so now that we have defined what is the distribution function and what is the probability density function, so we are now in a position to start talking about what is the random variable in the context of a continuous distribution. So, accordingly we revisit random variable in this setup now. So, accordingly, I will first talk about, so let omega sigma be a measurable space, right. So, a function x from omega to r, that is a real valued function defined on the sample space R, is said to be sigma measurable if the inverse image of every open interval is in sigma. Remember that sigma was a collection of subsets of omega. So, what I am saying is that if it turns out that a function x which is defined from omega to r is said to be sigma measurable if the inverse image of every open interval. So, any open interval in R from here, if the inverse image of that belongs to sigma, then we say that this function x is sigma measurable. So, in other words, x inverse of any open interval a b belongs to sigma. Okay. So, a measurable function, so we now a measurable function on omega sigma is also called a random variable. So, that is your definition of random variable in the continuous time setup. Further, we consider the probability space omega sigma p and x being a random variable on omega sigma, the measurable space omega sigma, then this random variable x defines a distribution function which will denote by capital F subscript x and a corresponding probability measure p subscript x or not, just like we had done in case of the finite case, by, and I will denote this by f x of t is going to be p subscript x minus infinity close t, which is the same as probability of x being less than or equal to t. So, then it brings us to the definition of what is independence of random variables. So, accordingly we can now talk about the collection of random variables, and in this case we talk about random variables in the continuous time. So, the collection of random variables capital X 1 through x n defined on the measurable space omega sigma are said to be independent if the probability of x 1 less than or equal to t 1 all the way to x n less than or equal to t n, this is nothing but the product of the probabilities of x I less than or equal to t I is equal to 1 to n. So, just to sum up what we have discussed today, we talked about probability space, we talked about a finite discrete probability space, and then we extended this to general probability space. We talked about what is the probability mass function, probability density function, the distribution function, and we discussed the definition of the random variables in both the setups along with the definition of independence in both the discrete and the continuous time setup. In the next class, we will talk about the moments in the probability space framework, and namely we will talk about the first two moments, the expectation and the variance, and we will talk about covariance and correlation coefficients, and we will discuss some of the other properties pertaining to them. Thank you for watching.